So this solution session, we are going to solve 2022 AMC 10B problem 1 through 10. Problem 1, also 12B problem 1. So this problem is a operation problem. This operation defined as absolute value of x minus y. So as usual, and we would like to start with the parentheses, right? And starting with this parenthesis and also this one. So I'm going to say 2 absolute value 2 minus 3. So absolute value 2 minus 3, that is always positive, which means 1. Then I will also focus on this 1 operation 1 minus. Now I'm going to do first absolute value 1 minus 2. Absolute value 1 minus 2, we can see that negative 1 and 1. Then 1 comes from the first parenthesis, operation 3. Now I'm going to focus on so what is 1 operation 1? That's absolute value 1 minus 1. Then what is 1 operation 3? Absolute value 1 minus 3. We can see that this is going to be 0. And we can see that this is going to be absolute value. So 0, technically, let's say, plus negative 2 will be my final answer. Okay, yeah, that is. Dr. Junaid, would you like to add something to this solution? So that's clear, number 1. I hope all 10B and 12B participants engage and solve this question. Okay, very nice. So let's take a look at the geometry, nice geometry problems. Okay, rhombus. Rhombus reminds us all 4 sides are equal. So I will put this one also, this side is also equal. Let's see. We can see this perpendicular. In geometry problems, we need to really process all the information, right? So now don't miss anything. AP is 3, PD 2. That's interesting, the row, not the scale. What is the area of A, B, C, D? So 2 plus 3, or 3 plus 2 gives us one side of rhombus, which is 5, 5, 5. It's very good. Then I'm going to focus on these triangles. So this triangle, of course, we see the perpendicular, and the perpendicular one reminds us Pythagorean triples, which is 4, 5, 3, 4, 5. In this case, 5 on hypotenuse, that means the other side, BP, becomes 4. So what is the area of rhombus? Area of rhombus is same as area of parallelogram, which is base time height. In this case, that's going to be 5 times 4, which is 20. This is good. Yeah, that was 12B problem 2 as well. Now, 10B problem number 3. Dr. Junaid.
Okay, great. Yeah, let's take a look at this problem. So we're going to have to figure out how many 3-digit positive integers have an odd number of even digits. And sometimes when you have counting problems where you have a lot of ways to do it, it's good to use a casework approach where you divide it into cases. So we can say case 1 If you're going to have an odd number of even digits, then maybe you just have one even digit. Okay, so if you're going to have one even digit, there's going to be different ways of arriving at that. Okay, so you can have even, odd, odd. Okay, you can have odd, even, odd, and you can also have odd, odd, even. In all three of these cases, we have a single even digit, which satisfies the problem, odd number of even digits. Now, we know that the number, if you start with the even digit, we can't start with 0. So we can only use 2, 4, 6, 8. So there's only 4 options here. But for odd, we have 1, 3, 5, 7, 9. So we have 4 times 5 times 5, which is going to be 100. Here, since we're starting with the odd, we can use all 5 odd numbers. We don't have to worry about starting with 0. And for even digits, of course, we can use 0 now. So we have 0 to, let me write that a little neater, sorry about that. So we have 0, 2, 4, 6, 8. So we have 5 times 5 times 5 is 125. Okay, similarly here, we have 5 odd numbers, another 5 odd, another 5 even. So we're going to have 125 ways to do this. Now, another way that we can have an odd number of even digits is we can also have 3 even digits. So we can consider that case. And there's different ways, you could divide this into 4 cases, or you could divide it into 2 cases, and case 1 has 3 subcases. Lots of ways to do it. As long as you keep careful track, you'll be fine. So let's talk about 3 even digits. So for 3 even digits, what you're going to have is even, 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 and we have to be careful again. Although 0 is an even digit, we cannot start with using 0. So we can only use 2, 4, 6, 8. So we're going to have 4 times 5 times 5 here, which is 100. Okay. So if you add up these numbers that we have here, we're going to get 450 for our answer. Okay.
Yeah, that's very good casework problem. Thank you, Dr. Junaid. That was great solution. Now this is a problem number AMC 10B, problem number 4.
Okay, yeah. So let's take a look at this problem. For these kind of counting problems, you have to be very careful because you don't want to do all this work and then be off by 1. So you have to be extremely careful. So what I like to do is, let me turn my annotation on. Sorry about that. Okay. So let's go ahead and take a look. At 4 o'clock, we know that the first hiccup occurred. Okay. And then let's think very carefully about which hiccup occurred at 4:01. Okay, we got to be very careful here. It's very easy to think that the hiccups are occurring every 5 seconds. So it's very easy to think that the 12th hiccup occurred at 4:01. Okay, but what you want to think about is you're already counting 4 o'clock as the first hiccup. So 4:05 is the second hiccup, 4:10 is the third hiccup, etc. So if you're very careful, you will realize that the 13th hiccup occurs at 4:01. Okay. And if you need to write it out and make it very clear, that's fine. It's better to spend a little extra time and be careful than to rush through it and think that it's the 12th hiccup. Okay. So the 13th hiccup occurs at 4:01. And similarly, what's going to happen is at 4:02, you're going to get the 25th hiccup. Okay, again, if you need to convince yourself, take your time and think about every 5 seconds a hiccup occurs. So in that 60-second interval, you're going to have 12 more hiccups occur. Okay. And then we notice an interesting pattern. Okay. We notice that every time it's going up by 12. Okay. Every time a minute goes by on the left, the total number of hiccups is going up by 12. Okay. So if we were to let N be the number of hiccups and M be the minutes past 4 o'clock, we can kind of figure out a nice formula. Okay, for example, since we're adding 12, if you do 1 minus 1 divided by 12, you get 0. If you do 13 minus 1 divided by 12, you get 1. If you do 25 minus 1, which is 24, and divide by 12, you get 2. So it's not too hard to come up with this formula. Okay, write that a little neater, sorry. N minus 1 over 12 equals M. Again, what does M represent? The number of hiccups that have occurred, and M is the minutes past 4 o'clock. Let's try that out. If you plug in N equals 1, 1 minus 1 is 0 over 12 is 0. It works because we have 0 minutes past the hour. Okay. And if you were to try 25 for N, 25 minus 1 is 24, over 12 is 2, you get 2 minutes past the hour. So what we've done is we've listed out very carefully a few of them until we found a pattern. And then we tried to, instead of going all the way to 458, which is a lot of writing, then we try to write a formula for that pattern. So notice that all the answer choices have 458, okay, which means all the answer choices have 58 minutes past the hour. Okay, keep in mind that 58 is our M. Okay, so we're going to let M equals 58, and we're going to solve for N using our formula. Okay, so we're going to get N minus 1 is equal to 58 times 12. Okay, and if you do 58 times 12 by hand, then you're going to get 696. Oops, let me fix that, sorry. Right, you're going to get N minus 1 is 696, which means N is equal to 697. Okay. So what that means is if we had gone to 458, that would have led us to the 697th hiccup. Okay. Now we want the 700th hiccup. Okay. So we're going to have the 698th hiccup. We're going to have the 699th hiccup. And we're going to have the 700th hiccup. Okay. And each time we know that we're going to add 5 seconds. Okay. 5 seconds here, plus 5 seconds here, plus 5 seconds here. Okay, because after the 697th hiccup, which is at 458, we still have to do 3 more hiccups to get to the 700th hiccup. Well, each hiccup is 5 seconds, so you're going to end up adding another 15 seconds. Okay, so our final answer is going to be 458, 15. Okay, because you're going to have to do the 15 seconds after that. Okay, very good.
Yes, thank you. That's great. Now we are solving 10B problem 5. So I'm going to approach this problem by first making one single fraction of each of them. The first one is going to be, we can see 4 over 3. And then this one is going to be 6 over 5. 1 and 1/5. 1 and 1/7. 1/7 is going to be 8 over 7. And I can see that this is also equal to 1 minus 1 over 9. This one 1 minus 1 over 25. This one 1 minus 1 over 49. And I can express this bottoms as one single fraction for each one as well. That's going to be 8 over 9, 25, 4 over 25, and 48 over 49. So be careful, this is inside the radical. So what I can write here equals, the top part is going to be 4 over 3, 6 over 5, 8 over 7. The bottom part become become square root of 8, 24, 48, and I'm going to remove 9, 25, and 49 from the radical. So that's going to be 3, 5, and 7. The good things about the 3, 5, and 7, these are the same unit, and we can get rid of numbers. So we have so leftover one on the top, on the denominator, 4, 6, 8. On the numerator, that's the small thing. So I can see that 48 is 24 times 2. That gives me 24 and 16, which is 4 times 6 times 8, which is 24 times 4. Where 4 comes from? Square root of 16. Now my final cancellation is going to be this is 24. Then finally, finally 8 over 2, 8 over 4, 2 will be my final answer. So that was the question 5. Okay, now question 10b6, also 12b number 3. That's interesting prime number problem. Let's see Dr. Junaid's approach.
So yeah, it's very tempting. You know, we know a lot of divisibility rules. We know the shortcuts for knowing divisibility by 3.
Yes.
Divisibility by 9, 11.
Divisibility by 11 especially, we can think of these numbers.
Yeah. And it's tempting to dive in and start adding the digits and or alternating addition, subtraction, and figuring out what's divisible by 3 and 11. And then, you know, you might start working with 7 and 13, 17, 19. Eventually it might get really, really tedious, right? So sometimes when you start going off in a direction where it's getting very complicated, especially for an early problem like this, there might be some trick, something very subtle that if you were to notice, the problem becomes very easy. And I'm going to share that with you right now.
Yes.
So when you write 121, you can write that as 110 plus 11. Okay, that's going to give us 121. And let's see if, because what I noticed when I thought about it is if you take something like this, you know, and then you add something like this, you know, what's going to happen? Well, fine, you know, I can put zeros over here. That's fine. You know, what's going to happen when you add them? You're going to get 1, 1, 1, 2. Oops, sorry. 1, 1, 1, right? And that's kind of the key thing, the realization, I think, that really unravels the problem. That you can write these numbers up here as additions of things that are very similar, but they overlap here, giving you the 2. And what's amazing is that this number here is the same as this number here, which means this number and this number are multiples of each other, right? Which means you can do some factoring. So let's see if we can use this observation and see if how that applies and what that leads to. So if we do 1, 1, 2, 1, 1, okay. So let's say we did 1, 1, 1, 0, 0 plus 1, 1, 1. Okay, does that work? Let's take a look. Well, if you add this, you're going to get 1, 1, 2, 1, 1. It works.
Yeah, 2 in the middle and then 1, 1. Yes, that works.
Exactly. Yeah. And then we kind of look over here. We're like, okay, I had 2 1s and now I had 3 1s. This guy here should have been an 11. Let me fix that before anyone.
Yes. 11. Yes. 11. Yeah.
So the pattern we notice is there's 2 1s here and 2 1s here, 3 1s here, 3 1s here, and every time we're increasing the zeros by 1. Yeah. So let me So let's see if that works again. So let's say we do 1, 1, 1, 2, 1, 1, 1. Increase the ones by 1, so now I'll have 4 ones. Increase the zeros by 1, so I'll have 3 zeros, and then I just stick with that 1, 1, 1, 1. Okay. So is that working? If we get 1, 1, 1, 2, 1, 1, 1 in that case?
Yeah, I think so. It's working.
Yeah, it's working. So now let's see what that means here. So now we get 11 times 10 plus 1 here. Okay. Yeah, thanks, Dr. Kanbir. Yeah, that makes it easier to see the pattern. Thank you. And here we can factor out the 111, and we're going to get 100 plus 1. And here we can factor out the 1111.
Yes, that's very good. So
we're going to get 1000 plus 1, right? So we can see that all the numbers are composite. Okay, so the first number is a multiple of 11, second number is a multiple of 111, third number is a multiple of 1011, etc. Or you can also say the first number is a multiple of 11, the second number is a multiple of 101, the third number is a multiple of 1001. Regardless, they are thus all composite.
wow, that's very nice solution. Thank you, Dr. Junaid. So you come up very interesting and so nice solution. So thank you. That's great. So this is 10B problem 7, 12B problem 4. It is a nice quadratic problem. So what are the key things we need to be careful about? We are looking for K and constant K, and our equation here, x squared plus kx plus 36. And this is also another key, 2 distinct integer roots, not 1, 2 distinct integer roots. So for this problem, I can take a look at the idea here, 2 roots, m and n, but thinking about m plus nx plus m times n, right? Focusing on the last numbers, the product of yes, the 2 numbers. I'm going to focus on the last numbers product, 1 times 36. And I am also focusing on the k. So if we have 136 creates 2 k's, which is it's plus minus, right? Then negative plus 37, and also negative minus 37. So there's 2 value. It could be -1, -2, 18, 3, 12, 4, 9, 6, 6. Let's see, 2 and 18 creates 2 k values, which is plus 20 and minus 20, right? And also 3, 12 creates plus 15, minus 15. It goes to middle, right? M plus n. Then what about 4 and 9? 4 and 9 creates plus 13 and minus 13. But we have to be careful about this guy. 6, 6. When I think of the 6, 6. So let's think about the 6, 6. What it is? 6, 6 would be plus 12x plus 36. Minus 12x plus 36. So what this equation tells us, this is actually contradict to this giving situation, 2 distinct integers. Why? Because this is complete square. That means only this last situation creates only 1 root, 1 equal root. That's why we don't, we are not taking this one. This is not the case. Then I am going to just pick this 8 constant k value. So that's the answer of number 7. Now let's go to number 8, 10B number problem number 8, and 12B problem number 6.
Okay, so let's take a look at this problem. What you want to realize is really all you're doing is you're taking the numbers from 1 to 1,000 and you're dividing them into groups of 10. So you have the first 10, the next set of 10, the third set of 10, etc., up to the last set of 10. And we want to know how many of these sets contain exactly 2 multiples of 7. So a lot of times when you start these problems, it's good to just, try to make a list and see if you see a pattern, and you'll get insights, and then you see if you can figure out what the overall answer is going to be. Just to make the notation a little nicer, I'm just going to denote each set by its first element. Okay, so we can say that the first set starts with 1, and we know that set has exactly 1 7 in it.
1 7, yes.
Yeah. Now the next set starts with 11, which also only has a single 1 in it.
So 1, yes. 21.
Yeah, exactly. The next set starts with 21.
We have to be careful. 21, how many? 21 and 28, 2, right?
Yeah, exactly. So we're going to have 2. And now if we go to 30, and what I'm doing, I'm just listing with the hope that, I start seeing some kind of a pattern. So with 31, what are we going to have? Yeah, just
1.
5 is 1, right?
Mm-hmm.
And with
41, 42, and 47, 2, yes.
Very good. So far, I don't see a pattern. And then 51, what are we going to have?
Just 1.
Okay.
61, just 1.
Yeah, because you're only going to have 63.
Oh, and then 70, right?
70, yeah. So we're going to have 2 over here. Okay. And then if you go on to 71, you're going to have
1.
Okay. Now, we can keep going with this. I won't go too much further. I'm about to show you what the pattern is. I'll talk about that. So here, what are we going to have for 81? Is it going to be 1 again? Right. We're going to have a
yes, 1, right?
And by the way, just to remind everyone, what do I mean by 81? I mean numbers from 81 to 90. Okay. So instead of writing that out, I'm just signifying each set by its first element, or lowest element, I should say. And then
in 91 and 100.
Yeah, so between 91 and 100, we're going to have 2. And if you could keep going, and you might eventually notice a pattern. But what you want to remember, if you've done these kind of problems, is you want to remember that patterns related to modular arithmetic and LCMs, right? We have these sets of 10, and we have multiples of 7. So it's, least count multiple of 7 and 10 is 70. Another way to think of it, when I first looked at it, is that over here, this is the first time we're starting with the multiple of 7. But when you, do we have another multiple of 7 anywhere in this list? Right? Does anyone see it? Anyone see another multiple of 7?
91 probably.
Yeah, 91, right?
7 times 13.
And what's going to happen is that, with these multiples of 7, we know over here that this block, okay, this block over here, that pattern is just going to repeat. Okay. Is this going to repeat? Because now we're getting back, once you get back to 91, if you re-envision this problem mod 7, okay, if you were to take everything here and just change it to mod 7, then it makes sense that this 21 is like starting at 0, because 21 mod 7 is 0. And it makes sense that this 91 mod 7 is 0, and everything else mod 7 is just going to repeat. Okay. So if you were to have this ability, let's say, to put on glasses and every number you just see mod 7, you're going to have that repetition occurring. This is going to happen over and over again. Okay. And another way to think about that is that you can even just look at it like this. Okay. I'm sorry, let me do it this way. Okay. So take a look at this one. This is the block of the pattern that's repeating. Okay. These are all of, we're looking at all the numbers from 1 to 70. Okay. Remember, this 61 means 61 to 70. When you look at all the numbers from 1 to 70, we have this wonderful block. And what confirms what we're doing is look at these first 3 numbers and look at the next block. It's the same numbers, 1, 1, 2. Okay. So if we were to do the next set, if we were to do 101 to 110, what do we expect to see? We expect to see this one pop up. Okay. And if it's good to play around. The way to get better at math is not just believing what you're told or you've seen. You get your hands dirty and you go ahead and extend it longer and longer until you really start understanding and believing that, yeah, this pattern really does repeat. You don't have to take my word for it, but with experience, you build intuition and you realize that, yeah, this first rectangle that has been highlighted is everything from 1 to 70. 70 is the LCM of 7 and 10. And that pattern 1, 1, 2, 1, 2, 1, 2 is just going to keep repeating. Okay. So let's go back to the problem. How many of these sets contain exactly 2 multiples of 7? So if you look at that rectangle that we've highlighted, how many of those first of all, how many sets do we have in that rectangle? We have 1, 2, 3, 4, 5, 6, 7. We have 7 sets of 10, 1 to 70. And 3 of those sets contain exactly 2 multiples of 7. So what we can say is if you were to look at the numbers from 1 to 70, okay, we would have 3 sets of numbers which would have exactly 2 multiples of 7. Okay, very good. Thank you. Similarly, if you were to go from 71 to 140, this is the next set of 70. Again, we would have 3 sets that contain 2 multiples of 7, right? What would come next? The next set of 70 would be if you were to go from 141 to 210. Okay. Again, you would have 3 sets of that contain exactly 2 multiples of 7, right? And we want to go all the way up to 1,000. So each block of 70 contains 3, and we want to know how many blocks of 70 fit into 1,000. Well, that's like doing 1,000 divided by 70. 70 times 14, what are you going to get? You're going to get 980, right? Right. So that means over here, if we follow it, we will eventually get to 980. Okay. Notice this is 70 times 1, 70 times 2, 70 times 3. And the 980 is what? 70 times 14, right? Over here, we're going to have 14 sets of 3. Okay. 14 times 3 is going to be 42, right? And of course, if you think about, what's going to happen next, right? You're going to have 981 to 990, right? If we were to continue, because we don't want to stop at 980, we want to go to 1,000. And if we continued again, we'd get 991 to 1,000. But we know what happens after that. We know that the next 2 things are just 1 and 1. Okay. This is what's going to happen here. Each of those, and if you weren't sure, you can check it by hand. You could find that there's a single multiple of 7 between 981 and 990. But once you get this repetition, you kind of know that you're going to have 1 and 1. So that's why we end up with the final answer of 42.
Okay. That's a great solution. Thank you for sharing. 10B, problem number 9. So now this is kind of telescopic sum types of problem. I would like to show my solution first. So when I think of this one and one more, that means it reminds me k over k plus 1 factorial, right? Of course. But so for the when it comes to telescopic sum, we need to make this what we call the fraction decomposition. We need to make into two fractions. So to do that, I'd like to do a little trick. The trick is plus minus 1 to make this one single fraction into two fractions. Let's see how it works. K plus 1 over k plus 1 factorial minus 1 over k plus 1 factorial. So when I do this one, I can notice that this is k plus 1. This is k plus 1 times k factorial. Then I can see that this is cancel each other out, and 1 over k factorial minus 1 over k plus 1 factorial. So then I can start by putting k equals 1. What happens when my k equals 1? 1 over 1 factorial minus 1 over 2 factorial. What about k equals 2? 1 over 2 factorial minus 1 over 3 factorial. What about k equals 3? 1 over 3 factorial minus 1 over 4 factorial. And finally, what about k equals 2021? 1 over 2021 factorial minus 1 over 2022 factorial. So what's going to happen when, that's why the telescopic sum really help us to, do you see that, get rid of this plus, minus, and this one will go previous one. Then this sum will be 1 minus 1 over 2022 factorial, which is this one can be expressed A, this one B, then A plus B is going to be 2023. So then I'm going to Dr. Junaid, you are a really good pattern seeker, and I see. So you mentioned you have another solution for this problem. Would you be able to share? I'm going to erase this one and then give you space for you to share your nice pattern solution. So I like that solution as well.
Thank you very much. I like your solution very much. Very much. It was a very nice solution. So when I saw this problem, what struck me was that, you know, this 2022. Oops, let me turn the annotation on. Right, I noticed that there's a 2022 here, and there's a 2022 in the answer, and that's probably not a coincidence. So what that kind of got me thinking was, you know, if this sum was not as long, if it had fewer terms, the answer would probably be corresponding. Okay, so for example, let's say this sum only went to 10, right? Then probably the answer choices would have been like 8, 9, 10, 11, 12, or something like that, right? So then what I kind of thought about was, if you were to just add the first two terms, 1 over 2 factorial plus 2 over 3 factorial, then you're going to get 1/2 plus 1/3, which is 5/6, which is 1 minus 1 over 3 factorial. Okay, that matches this structure. Okay, and in that case, you will get A equals 1 and B equals 3. Okay, but let's make sure that this continues. So let's say we were to add the first three terms. We'd have 1 over 2 factorial plus 2 over 3 factorial. Oops. plus 3 over 4 factorial, which is going to be the 5/6 we had before. Okay, keep in mind that this guy is the 5/6, right? And then I will have 3 over 4 factorial is 1/8, okay? And if I add these two guys together, I get 23 over 24, which is 1 minus 1 over 4 factorial, which gives me...
Yes, that's another one. And
A equals 1 and B equals 4. So then we figure out, yeah, so in our case, since we're going to add up to 2022 over here, we're gonna end up with A equals 1 and B equals 2022.
yes.
And adding that up, we get A plus B is 2023.
Yes, that's great. The definition, one of the definition of the MathTopia, the study of pattern.
Right.
So we have seen plenty of pattern in this first 10 problem. So that's great. Thank you. This is 10B problem 10 and 12B problem 7.
Okay, so for this problem, looking at the fact that these are 5 positive integers and looking at the answer choices for the least possible mode, the numbers are pretty small. It's very reasonable to take an approach where you try to play around with numbers and come up with the answer. The numbers are pretty small. And what we can do is try the answer choices starting from the least and try to find the first one that works. What's important is that since we have 5 numbers, if we were to list them from least to greatest, for example, let's say I'll just list something, 1, 2, 3, 5, 5, let's say, just to give you a feel of the problem. It says the unique mode of these 5 numbers is 2 greater than the median. Okay, so the mode is bigger than the median, and we know that that mode is going to have 2 numbers that are the same. There's only 2 spaces over here. So what does that mean? It means that the mode, the 2 numbers in the mode are going to be to the right of the median. Okay, the mode is greater than the median. So, we can kind of look at something like this to give us a feel of it. Okay. In the first part of the second sentence, they tell us that the mode is 2 greater than the median. Okay. In other words, the median has to be 2 less than the mode. So if we were to assume maybe answer choice A is correct, then we would put the 2 5s over here at the end. Okay. And then since the median is 2 less than the mode, we'd put a 3 over here. Okay. We don't know the first 2 numbers. That's fine. So for now, I'm just going to go ahead and leave 2 spaces over here. Okay. And again, this is necessarily the case if we assume that answer choice A is correct as the least possible value for the mode. You put the 2 5s at the end, the median is 2 less, you put a 3 in the middle. Let's see if this can work. If it can work, then we're done. Answer choice A is going to be our answer. Now, what's interesting is in the second part of the second sentence, they say that the median is 2 greater than the arithmetic mean, okay, or average. So if the median is 2 greater than the average, then that means the average would have to be 1 in this case, okay? And we know that when we multiply the average of a set of numbers times the number of numbers that we have, that product is going to give us the sum. So we have 5 numbers that average to 1, which means our sum is going to have to be 5 times 1 is 5. Okay.
Is it possible?
Yeah. I mean, we already have a sum of 13 just by looking at what we have here. There's no way we're going to put 2 positive numbers in the first slot and get a sum of 5. So A is not working for us. Okay. And similarly, what we can do, let me just clear it instead of that. Okay. Let's try 7. Keep in mind, we are assuming what the mode might be. Okay. We know the median is 2 less than the mode, which means we're going to put a 5 here. And let's think about if we can make this work. Can we find 2 positive numbers to put in the first 2 slots to make it work? Again, the average is 2 less than the median.
Which is 3.
Which is 3, which would give us what sum?
Sum is going to be 15.
Right? Because we need 5 numbers to average to 3. So we know the sum is 15. Can we get these 5 numbers to add to 15? Well, these numbers here already add up to 19. So we're out of luck. Okay,
Yes.
so that's not working.
That's not working.
Yeah.
B is not the option.
So now if we try to make the mode 9, the median is 7. We can see if we can get that to work. In this case, again, the average will be 5.
And sum 5 times 5, 25.
Right, very good. The sum will be 25. Now, if you add just the last 3 numbers, you already get 25. Okay, these already are adding up 25. We can't put 0 and 0 in the beginning. They have to be positive integers. So even C is not working.
Okay.
So hopefully one of these will work soon. So let's
That's good. Let's
Yeah.
see.
If we try 11 for the mode, they tell us that the median is 2 less than the mode, so that would be 9. And then we need to figure out this. The
That-
average is 2 less than the median, which is 7, which would give us what sum?
7 times 5, 35.
Yeah.
Okay, we are
Yeah. Now, if you add up these numbers, we get what?
11, 22, 31.
31, right? So now the question is, can we put 2 numbers here? They have to be positive integers, okay? They have to be less than 9, and they're going to have to make up the difference, which is 4. And we can put 1 and 3, okay, which add up to 4 plus the 31 is 35, and this will satisfy everything. All the requirements of the problem are satisfied. So that means that the lowest possible value for the mode is going to be 11. Yeah.
That's great. Thank you, Dr. That was great solution.
Thank you.
That was the end of the our first 10 problems. If you like to do more practice this kind of problem, AMC 10 and 12 problems, you can visit MathTopia Press books such as Art of Algebra and High School Math Challenge and Geotopia. Thank you for listening. I hope this session beneficial for all. Thank you.